Okay, so now let's take a look at the classification of optimization problems. It's very useful to understand the different types of optimization problem and the algorithms as well, because it helps you identify the most appropriate optimization strategy for your particular problem. Remember, we saw in the flowchart of how optimization is typically performed. Before we actually commit to doing the optimization, we want to first strategize, particularly for the kind of problem that we have at hand, what is the best algorithm or strategy or approach to use for it. So it's very important to understand this landscape of optimization problems. Now, let's take a look at the problem classification first. In terms of the problem formulation, we can classify in different ways, particularly for the design variables. We can have continuous design variables or discrete variables or a mixture of these two. So we have a mixed variable problem. We've been looking at continuous variables so far. So all of our design variables X, they can take whatever values 1.1, 1.213, 1.567. So it doesn't really matter. So it's a continuous variable. Discrete variables are sometimes more difficult to solve than continuous variables. One approach could be to convert it into a continuous variable and solve it as if it was a continuous variable. Then once you get a solution back, you then convert it back to a discrete variable. So it really depends on the nature of your problem, what approach you need to take. If that doesn't solve it, then you would probably need an algorithm that is designed particularly for discrete variables. And that goes the same for mixed variable problem as well. Then in terms of the objective, we can have a single objective problem or a multi-objective problem. So earlier, the examples we saw, they're all about single objective problems. But in engineering design, sometimes we have two objectives that we want to optimize for. For example, we want to minimize the cost and maximize the performance. And this essentially becomes the trade-off. For more money you pay, you can potentially get more performance. But the conflict between the two objectives, if you want to use a more mathematical way to express it, you can use multi-objective optimization to formulate this kind of problem. And for constraints, we can classify it in terms of whether it is a constraint problem or an unconstrained problem. We looked at constraints earlier with the different examples we have. Although constraints are very common in engineering design, the reason why we're also interested in unconstrained problems is that the way to solve it actually inspires a lot of other algorithms. So a lot of the times, especially when we go on to gradient-based methods, we'll see that to solve a constrained problem, we first use some techniques to convert it to an unconstrained one. Then we can use our typical algorithms to solve it and come up with the solution. So this is why we're also interested in unconstrained problems as well. Now, in terms of the functions, this could be the objective function or the constraint functions, or even the state equations, which are also functions of our design variables. They can also be characterized, and their characterization also affects how we choose the different algorithms to tackle them. So first off, we have a characteristic called smoothness. A function can be continuous, or there could be discontinuities within that function. Then this would be a discontinuous function. If you imagine having a surface plot like the 3D plot earlier, if there are any holes or if there are any irregularities on that surface such that it's not smooth as silk, then it is a discontinuous function. Now, typically optimizers can cope with discontinuous functions as long as the discontinuities are not very close to the optimum point. If it is, then you might not be able to use the regular optimization algorithms, and you must use a more specialized optimizer to tackle that kind of discontinuous functions. Another way to classify it would be the linearity. A function can be linear or it can be nonlinear. Linear functions just basically means that your independent variables, like the design variables we have, x1, x2, x3, they are not raised to a higher power. So you only have 1x1 or 2x1, 3x1, but there are no higher power terms in that function, so they are just linear. If you go back to the 3D surface plot function, objective function over there, we actually have cubic terms, then those will be nonlinear functions as well. And also, if you have any other terms like exponential terms, trigonometric terms, then that will also be a nonlinear function. Now, another way to characterize function would be modality. This is specifically about the objective function. We can have a unimodal objective function or a multimodal objective function. A unimodal objective function simply means that there's only one minimum or optimum. If we have a multimodal problem, then it means there are actually many or more than one optimal points. So if you imagine that we're minimizing a function, if there are multiple values in the 3D representation, then this means that there is more than one optimal point, then this becomes a multimodal problem. And we call all of this optimum simply local optimum or local optima, that the particular one that is the best out of all of this local optimum, we call it the global optimum. So the global optimum usually would be the final answer to a multimodal solution, but it's also important to identify all of the local optima as well. Now, another way to classify a function would be convexity. We'll look at convexity later on in the next lesson. Essentially, a function can be convex or non-convex. Convex functions actually represent a very small amount of functions that we'll look at, but they actually inspire a lot of other optimization algorithms that can deal with non-convex functions as well. The reason why convex functions are so special is because convex function is always by definition unimodal, as we'll see later on. So it means that the optimal solution we find will definitely be a global one because there's only one optimal point. And there are very strict requirements for a function to be convex, but if you can identify a function as convex, it becomes very straightforward, even trivial to solve it because it's a very well-defined function. Now, finally, we can also classify a function in terms of its stochasticity. So a function can be deterministic or it can be stochastic. So what does this mean? If your function is not just one single equation, but it actually comes with uncertainty, you might see some representations like a function has a mean and a variance and is described using a normal distribution, then that function is a stochastic function. The previous examples we saw before, they are all deterministic function, but if your inputs to your particular function is a random variable, for example, the height of a person in a society, that would be subject to a normal distribution. So it comes with mean and variance as well and other statistical descriptors, then that would be a random variable. And so the function will also be stochastic as well, with uncertainties propagated from that input to it. So it would have some uncertainties in it as well, then making it stochastic. Stochastic optimization is also another thing that we'll cover, hopefully in another series of this course, because stochastic functions are very useful in engineering design. We can use uncertainty or probability distribution to describe things like manufacturing defects or to describe the performance envelope of a particular product. It also enables reliable and robust optimization. So this is also a very big topic, a very useful topic as well.